In this video, we'll be taking a look at section 5.5, which covers right triangle trigonometry. So here we have SOHCAHTOA. SOHCAHTOA is a little mnemonic to help us remember that the sine of theta is given by the opposite side over the hypotenuse. Cosine of theta is adjacent over hypotenuse, and tangent is opposite over adjacent. And this is true if we are given a right triangle with an angle of theta. So if we have angle theta here, then opposite is the one across from the angle theta. Your hypotenuse is always the longest side, and that's opposite from your right angle. It's across from that. Your adjacent side is the one along your angle theta that's not the hypotenuse. So it's the one next to it, but it's still not the hypotenuse. So we're going to see if we can use some of this right triangle trig. Here I have a triangle with sides labeled 3, 4, and 5, and then we have angles alpha and beta. We want to see if we can find the sine of alpha, the cosine of alpha, the sine of beta, and the cosine of beta. So sine is opposite over hypotenuse. From alpha, the opposite side is 4, and hypotenuse is always across from the right angle, so that'll be 5. So our sine of alpha will be 4/5. For the cosine of alpha, that's our adjacent side over hypotenuse. We know that the hypotenuse is 5, so if we want to go adjacent to angle alpha, it can't be the 5 side, it's got to be the other side, 3. So adjacent over hypotenuse gives us 3/5. Now we're going to switch to beta. If we want the sine of beta, we have to do the opposite over the hypotenuse. So from beta, the opposite side is 3. And then our hypotenuse is still 5. And for the cosine of beta, our adjacent side is 4 because it's next to it, and then our hypotenuse is still 5. So our cosine of beta is 4/5. You may notice that the cosine of alpha is equal to the sine of beta, and the sine of alpha is equal to the cosine of beta. They call these functions cofunctions because of this property. We're not going to focus on it in this class, but it's a neat little thing if you want to do some research and learn about cofunctions. Now, as with every other math section, we need to do some application problems. So the angle of elevation to the top of a building in Seattle is found to be 2 degrees from the ground at a distance of 2 miles from the base of the building. Using this information, find the height of the building. I'm going to try drawing a picture. So we have the ground, and we have a building. It says that the angle of elevation is 2 degrees. Well, the angle of elevation is from horizontal, how much rotation do you need to do to see whatever you're looking for? So it's saying from the ground, you have to look up 2 degrees to see the top of the building. We know that this is measured at a distance of 2 miles from the building, and we are trying to find the height of the building, so I'll call it h. So we have our angle of 2 degrees. We're going to assume that the building is at a right angle to the ground because that's usually pretty acceptable. So if I know the angle, I'm trying to find the opposite and I know the adjacent. I think tangent's going to be best suited for this. So the tangent of 2 degrees is equal to my opposite side h over my adjacent side 2. Well, I'm trying to find h, so let me solve for h by multiplying both sides by 2, and I get that h is equal to 2 times the tangent of 2 degrees. 2 degrees is not one of my angles that I have memorized the trigonometric values for, so I'm going to use my calculator. And this is where it becomes very important to keep track of what mode your calculator's in. If I go to mode, I'm in radian mode right now. I need to switch to 2 degree. And I get 2 times the tangent of 2 degrees is 0.0698, give or take. That seems really short for a building. How does that make sense? Ah, the height of a building, that's a distance. And we measured distance in miles before. So that's how tall the building is in miles. Well, we typically don't measure building height in miles, so let's switch it to something we're more familiar with. 1 mile is equal to 5,280 feet. So if I take the height of the building in miles and multiply it by 5,280, I get that the height is about 368.763 feet. All right, next one. A 400-foot tall monument is located in the distance. From a window in a building, a person determines that the angle of elevation to the top of the monument is 18 degrees and the angle of depression to the bottom of the monument is 3 degrees. How far is the person from the monument? Let's make another picture. So it sounds like this person has to look up to see the top and look down to see the bottom. So if they're in this building over here, maybe they're about here. So they have the angle of elevation up, the angle of depression down. And these angles are measured from horizontal. They said that the angle of elevation is 18 degrees and the angle of depression was 3 degrees. And they told us that the height of the entire monument is 400 feet. They want us to find how far this person is from the monument. So I will say that we are trying to find their distance, and I'll call it D. Well, let's see if we can come up with any equations here. So it looks like I have 2 right triangles, one here and one here. So let's see if I can work with this top one. I really don't have a whole lot to work with. So let me say that this top part is X, from the top of the monument to the horizontal place where the person would look just straight out the window. Well, then this bottom part here would be 400 minus X, because the whole thing is 400. If X is above their sight distance, or the distance where they look, then 400 minus X is going to be below. So starting with this top triangle, I know something about the opposite side and the adjacent side. So that'd be the tangent of 18 degrees is equal to the opposite X over the adjacent D. That doesn't seem super helpful yet. Let's try the bottom triangle. The tangent of 3 degrees is equal to the opposite of 400 minus X over the adjacent D. Well, that doesn't seem super useful either. But let's use a method that allows us to solve 2 equations that have 2 variables in it. It's known as substitution. To use substitution, we have to get one of our variables by itself first. So I'm going to take this first equation and multiply both sides by D. Then we'll have D times the tangent of 18 degrees is equal to X. But now that I know what X is, I can plug it into my other equation. Let's see if we can run with that. The tangent of 3 degrees is equal to 400 minus what X is. We just said that X is D times the tangent of 18 degrees. And that's all over D. So I've just replaced what X is. I'm trying to solve for D, so I'll go ahead and multiply my D over to the other side. So we have D times the tangent of 3 degrees is equal to 400 minus D times the tangent of 18 degrees. Still trying to solve for D, so let me make sure that all of my terms with a D in them get on the same side, because right now I have one on the left and one on the right. So I'll add this one over, so that I have D times the tangent of 3 degrees plus D times the tangent of 18 degrees is equal to 400. can factor out the d, so that I have d times the tangent of 3 degrees plus the tangent of 18 degrees is equal to 400. And then I can solve for d by dividing both sides by the sum of these tangents. So d is equal to 400 divided by the tangent of 3 degrees plus the tangent of 18 degrees. Consult the calculator, make sure we're in degree mode. We are. So we're going to take 400 divided by, in parentheses, the tangent of 3 plus the tangent of 18. And we get that d is about equal to 1060.0871. And this time we were measuring our distances in feet. So this one actually gets to stay in feet. No weird computations here.